I'm going to share my slides. It's a great pleasure to be able to have this opportunity to talk to everyone. I think I see from the participant list that there are some old friends among many new friends, and it's a pity that I couldn't be able to attend there to meet everyone in person, face to face. But I think in future there will be more chances to do that after the COVID is finished. So the topic of my presentation is called Intelligent Corrosion Control via Data-Driven Approaches, which is one of the area that I'm interested in. I call it Intelligent Corrosion Control because nowadays we're facing more and more complex corrosion problems, and traditional way of design, traditional materials and traditional way of understanding materials degradation are not going to be enough for fighting against these type of complicated, ever complexing corrosion problems. And again, I'm from the National Materials Corrosion Protection Data Center, and also from Beijing-based Innovation Center for Materials Genome Engineering. Both of the institutes are associated with University of Science and Technology Beijing. And we like to say that materials are the backbone of manufacturing of everything, of the human civilization, but there are problems with their bottlenecks, major bottlenecks of materials R&D nowadays, because it takes a very long time R&D cycle to finish the materials research. The application usually takes 10 to 15 years and even longer, and it generates high R&D costs because it's really the cost behind these long R&D cycle and high R&D costs is really the fact that the methods to develop and apply materials are really trial and error and experience based. And we urgently need to have new methodologies that can transform materials R&D modes and shorten the cycle, reduce the cost. And for this purposes, national, international research plans have been developed to accelerate materials R&D. I think Dr. Jiang have mentioned that Materials Genome Initiative is quite known for it's a flagship initiative and planned research plan in the United States, and it also has a quite big impact around the world. And similarly, in Europe, Japan, many different countries have different national and multinational research plans that are aimed to develop materials in a faster way and at cheaper costs. So the basic idea of taking the Materials Genome Initiative, for example, is really to change the traditional trial and error research model and accelerate the development of new materials through really the infusion of new efficient methods. And the main target was called 2 halves, which is reduced the R&D cycle by half and also the cost by half. The key technologies involved in the Materials Genome Initiative are high throughput computational methods, high throughput experimental tools, and also the machine learning AI tools that can be used to predict the material's behavior and optimize material composition and learning materials composition, structure, behavior relationships in a more efficient way. And in China, we also have this National Materials Genome Engineering Research Plan, and it started almost, I think, more than a decade ago. And now it has, I think, 4 major building blocks for the Chinese MGE research plan. The first building block is the development of high efficiency materials computation design tools, including high throughput integrated autonomous computing methodologies for material science. And the overall aim of this track was to achieve a rapid and low cost screening and design of new materials, and also a more rapid exploration of new performances of these materials. And the second track was the high efficiency materials preparation and characterization based on high throughput automatic intelligent experiments. And the goal of this track was to achieve a rapid verification of new materials and rapid accumulation of materials data through efficient experiments under rational guidance. And also, there's a track dedicated to efficient evaluation of prediction technology, material service behaviors, and degradation processes. And the goal was to significantly shorten the material service evaluation cycle and improve the predictive accuracy of material service life. And I think my talk today will be more or less focusing on the third track. And the fourth element of the Chinese MTE plan was to develop MTE-ready database and big data technologies in order to provide intelligent data support for materials R&D. And
Professor, can I just interrupt just briefly? At some point, the sound quality is like not very clear. I'm not quite sure if you can sort of like be nearer to the microphone or can do something about that. Thank you so much.
Okay, yeah, I'll just stop the screen to make sure it's better. So the reason why we're interested in using the material freedom approaches to study corrosion is because corrosion is really a big problem, and it can seriously affect the service safety of infrastructures, equipment, and it can cause an economic loss of over $4 trillion per year globally. And one of the major bottlenecks faced with all the corrosionists is to develop next generation corrosion-resistant materials that can fight against more complex and more extreme environmental conditions. And this is a common problem that are in energy, transportation, constructions, urban space, and all type of industries. And corrosion or degradation of material, environmental degradation of materials, is complex problems that are affected by many different factors. And for example, there are not only all sorts of materials factors like element composition, processing, structure, surfaces, and also there are also environmental factors because for the degradation to occur, there has to be environments like humidity, temperature, radiation, stress, different kind of corrosive ions. And because of such complexity, it takes a very long time. Actually, it takes I would say the longest time and highest cost during the whole chain of materials R&D and application. This is especially true for developing materials with high corrosion resistance, where durability is really a big criteria. And traditionally, the corrosion resistance of the materials are evaluated based on two major categories of methods. The one is outdoor exposure test, which is simply by putting coupons, large size coupons on a particular environment. And after a certain time, we retrieve the coupon, analyze it, and understand how much it degrades. This type of test, as you can imagine, is really time consuming, and it takes years, decades to finish the degradation test because corrosion is the time consuming process, and it also is costly. And what's even worse is that even after we have decades of years of data accumulation, and usually we'll have only a fragmented data, and the data are poorly coupled with the dynamic changing environmental factors. And also we have this type of indoor acceleration test to study the corrosion resistance. And in these type of test factors such as temperature, humidity, radiation, or corrosive media, it can only be changed in a very single monotonous way, which is very different from the real dynamic service environment. Currently, the material research community focuses on more on the influences of composition, structure on the corrosion thermodynamic processes, while the research on the influences of environmental factors and their complex coupling effects on the dynamics of corrosion processes is very limited. In China, we began to study the mechanism of corrosion in different type of natural environments, in soil environments, seawater environments, atmospheric environments, in a long time ago, more than 70 years ago. And in the 80s, we already established a nationwide network of test stations in different parts of China to study the degradation behavior of different materials, structures, equipment, infrastructure over time. And in the 90s, such kind of initiative has become quite a major project supported by all kinds of governmental agencies in China, national governmental agencies in China. After 7 years of development, in 2019, we have been certified as one of the 20 national data centers in China. We have data centers on microbiology, on earthquakes, on astronomy, on human health, but also we have one particular data center, national data center, focusing on the degradation and service performance of materials. And our center has integrated materials environmental corrosion protection data production sources from 20 nationally certified field stations and a large number of test sites. And we have actively collaborated with different parts of the world for data sharing, for doing similar kind of testing, for standard development as well. So far, we have conducted long-term corrosion tests for up to 35 years and have accumulated over 30 million corrosion data for 800 types of materials, including steels, non-ferrous alloys, concrete, cements, coatings, and polymers. Even though that's 30 million data, does not really sound like a big data set, but the data that we have obtained for these type of data sets are all obtained after long-term corrosion test, the field coupon corrosion test. So basically, each data would take at least 1 year. Normal, average speaking, it takes about 5 to 8 years to get just one data. Recognizing this kind of limitation in the capability of data acquisition, we have, in the past decade, we have been updating our network by developing corrosion online monitoring system that integrates new monitoring technology and sensors, and also the Internet of Things platform to carry out a high throughput collection and real-time transmission of the materials environmental corrosion data. We have developed a variety of new corrosion sensors that can achieve a long-term continuous monitoring of not only corrosion data, but also the coupled multiple environmental parameters, and not only substantially increases the amount of the size of the data set that we have from the corrosion test, but also the corrosion data are better coupled with the simultaneously collected environmental data. And these type of sensors have been used in many major industry sectors in China and has been shipped outside of China for international collaboration. And once we have collected a lot of data, I think that the more important task was to find a way to better store and utilize these type of data. And since almost 20 years ago, more than 20 years ago, I think, we have been working on a construction of database software and data sharing network for corrosion data. And in 1994, we developed the first generation of standalone database software for prediction of carbon steel corrosion behavior based on an expert system. And in 2004, the second generation becomes online. It's a web-based software. And in 2009, all the environmental data, corrosion data from the national corrosion sites are integrated into this third generation website for data sharing. And in 2013, the fourth generation becomes more comprehensive, and it's really becoming a gateway for Chinese corrosion protection researchers And each year we have over 1 million visitors from Hispanic or other countries. In the last decade, with the emerging MGE or Material Genome Initiative research community, we have also worked on quite a lot on using the data mining, modeling, and visualization technologies for more efficient data processing utilization. This is also because that we have more data and we need better tools to process these data. The goal of such kind of initiative was to model and predict the complex, really complex composition, structure, erosion, environment relationships, and accelerate the R&D and insertion of advanced, better corrosion-resistant materials. And we have developed a concept called corrosion big data as a general framework for our research, which includes 4 basic elements. The first one is the high throughput acquisition of multi-source heterogeneous corrosion data. And the second one, once we have the data, is a multidimensional intelligently associated database construction, because we want to have newer databases that are machine learning friendly. The third element was the data mining, modeling, and visualization, which is which is the the topic today. And the third elements was the ones we have the first 3. We want to design a data sharing platform that can be used for different applications, different industry sectors for their accelerated material design and selection, and smarter corrosion monitoring and safety management. And it's kind of like if you consider data as money, so it's really like getting the money, saving the money, developing a way to better using the money, and then to use the money in a proper area to have the highest benefits and return of the investment. Like I said earlier, corrosion data is a complex problem. So corrosion data are also a little bit different from materials data, because there are numerous mutually influencing corrosion environmental condition parameters. So corrosion data, we consider them to have relatively high dimensions, and also these dimensions are influencing each other. So directly applying the high dimensional corrosion data for machine learning model will likely reduce the efficiency, accuracy of the model because of the redundancy and also the collinearities between the high dimensional attributes. And that's why we kind of take a 2-step approach to process and use our data. The first step is that we use correlation-based or totality-based analysis to identify the key corrosion influencing factors from all kinds of factors that can affect corrosion. And once we have the key factors, we use them as inputs and use the degradation rates or corrosion rates, or the degree of corrosion as the outputs, and develop machine learning model for corrosion prediction. We also use our algorithm social tests for different experimental tests for verification. And these are the models that we use for algorithms that we used for reducing the dimensionality to get the right features for the models. And these are the algorithms that we have used for the machine learning corrosion prediction models. And depending on the origins and the characteristic of the data sets and the models, the algorithms that we have used are a little bit different. For example, for the outdoor corrosion coupon test, they have the characteristic of small data size and high dimensionality, but really high dimensionalities. But for a corrosion monitoring test, they have big data sets, and the dimensionality or the influencing factors are normally lower than outdoor coupon test, and they also have quite large noises from the monitoring because of the environmental perturbation. Next, I want to show a couple of case studies to exemplify why and how we can use machine learning model to better treat, better process corrosion data to get the information in a more efficient way. The first example is the development of predictive maps for atmospheric materials degradation. And this is an ongoing project that has been taking place for really more than decades, and it's still going on because the material systems are evolving. And we have applied, exposed typical metals, polymers, organic coatings. And in this particular case, it's in 13 atmospheric sites across China. And we have collected comprehensive degradation data such as corrosion rates, and aging index for polymers, adhesion loss, or electronic impedance spectroscopy data for coatings. And we have also simultaneously collected the environmental data during these exposure tests. And also, we have obtained atmospheric environmental data from 804 data cities in China to have 13 meteorological parameters to show the environmental features of different parts of China. First of all, we applied a Pearson correlation analysis, factor analysis, to identify the similarities between environmental factors, and also to reduce redundant information between the different environmental factors based on the data obtained from the 13 test sites. And next, we applied a gray correlation analysis between the environmental data series and the corrosion degradation data series, also obtained from the 13 test sites. And after these three steps, we have been able to identify that this is for a particular type of polymer, that the most important key features that affect the degradation is humidity, maximum temperature, the summation of rain time, and also the summation of sun irradiation. And we have put the four key environmental factors as the input, and also the degradation rate of some of the polymers at the certain test sites as the output, develop a neural network model. And after the model is developed, we feed the model with the four key environmental factors from the 804 cities in China. And we get the prediction one by one and project them on a Chinese map, and using Perkin interpolation to fill in empty spaces between different data, different predicted points. And now we get a map showing the variation of degradation degree for the type of polymers around China. And similarly, we have used the same methodology to treat metals. And this is the corrosion prediction of three types of low alloy steels in atmospheric environment in China. These two are for carbon steels, and these are two types of weathering steels. And we can see that the environmental factors, the key factors, are different compared to polymers. For the carbon steel, we see that after 4 years of exposure, in certain areas in China still show quite high degradation corrosion rates for carbon steels. But for the weathering steels, after 4 years of exposure, the corrosion rate has been significantly reduced because of the formation of protective rust layers on the weathering steels after environmental exposure. In a second case, as I mentioned multiple times during this talk already, the corrosion data has high dimension, large dispersion, and also poor continuity, which prompted us to think about that a random forest model based on decision trees could be a better solution to treat this type of scattered data, especially for the data obtained from a coupon exposure test. What's more important by quantifying the importance of covariates on the corrosion rate by measuring the effect of perturbations at the input site on the output area, we can also know the importance of particular attributes or the factors that are affecting the corrosion. And this is, I believe, is another way of identifying the key features, key parameters for corrosion. And in this example, we developed an advanced random forest model called dense cascade weighted care nearest neighboring random forest deep learning model, which is aimed at better finding the complex relationship between dispersed data sets from the atmospheric corrosion coupon test data. And here, the data sets are long-term exposure tests from 17 type of alloys at 6 outdoor locations in China, and the inputs are 13 chemical composition of the steels, and also the 17 environmental variables. And the output is the corrosion rate. And by comparing the different type of algorithms, we can definitely see that random forest-based models are definitely better than neural networks, full vector regression, linear regression, because of its better ability to treat dispersed, discrete data sets in a high dimensional space. And also, we can use random forest model to quantitatively evaluate the contribution of materials composition and the environmental parameters on the materials failure. And this is kind of based on the causality rather than correlation analysis, which we believe is a more scientific way or understandable way to do the dimensionality reduction. And on the top, on the right-hand side, we can see that during the 16 years of exposure tests, in the first year, environmental factors are really playing a dominating role on the corrosion rates. And even after 16 years, it's still a lot more important than the materials composition in terms of the importance to the corrosion rates. And over the 16 years of exposure, the importance of materials composition has become more and more important. And this is because the formation of corrosion products that kind of bring the compositional effect from the bulk of the metal to the surface during the exposure tests. And this is showing the variation of the importance of different parameters like chloride, rainfall, pH, or humidity, temperature during the 16 years of exposure. And the previous two examples are mostly focusing on using materials, environmental factors as input and using corrosion rate as output. And we can also use similar concept by using materials composition as input and corrosion resistance in terms of corrosion potential, corrosion current densities, and passivation range, pitting potential, different type of corrosion parameters as the output for a design and optimize the design of corrosion resistant alloy. And this is showing the model, the visualized model where we can better identify the best composition that can give us the highest corrosion resistance. In a third example, instead of using random forest models to treat corrosion coupon exposure tests in small data sets, we're using random forest model to process corrosion monitoring data and generated from a galvanic couple-based corrosion sensor deployed in a coastal city in China, in Qingdao. And the basic idea of this sensor is that it's based on carbon steel as anodes and graphite as cathodes, or copper as cathodes. And once there are condensation of water on top of the surface, it completes the surface and generates current. And after 1 month of exposure, we have obtained more than 100,000 data just from this one particular sensor. And for the model, the input variables are the the rainfall status, temperature, humidity, and also a lot of different type of pollutants that have been varying during the 1 month period. And the output are the instantaneous current generated from the sensor, which is a reflection of the corrosion, instantaneous corrosion rate. And before the actual modeling, we have applied a data cleaning step to filter the noise intrinsically associated with the corrosion monitoring data. The concept or the principle of the cleaning step was based on frequency. We consider the low frequency are the real corrosion data, but high frequency are the system error and the perturbation from the intrinsic system and environment. And even after the data cleaning part, we can see that it's really impossible for us to see any trends from clearly from the original data, including the current, the temperature, humidity, rainfall status, and different sorts of pollutants. But after we feed the data into a random forest model, we can see that during that 1 month of corrosion test, the most important 3 parameters on the instantaneous corrosion rates are temperature, rainfall, and humidity. And even though that this sensor is placed in a coastal city, chloride condensation is not really important for the first month, but afterwards, after one month, it becomes more important, and the importance becomes significantly important. It is significantly high after approximately 1 year of exposure for the chloride condensation. And from this, we can learn that the chloride condensation is a temporal process and is a cumulative effect on the corrosion rates. And next, we want to show the variation of the importance of temperature, rainfall, and humidity during the 13 days of corrosion tests. And the dark green are the importance of the rainfall, the light green are humidity, and the purple one are the temperature. We can see that the importance of temperature was somewhat stable during the 1 year test, but the 1 month of test. For the humidity, it started very low and not stable during the first 10 to 15 days. This is because that in the first 10 days, the sensor surface or the material surface are still quite clean, and it's difficult for a clean metal surface to efficiently absorb atmospheric moisture to form a layer, water layer that generates corrosion currents or corrosion rates. So at this point, really, I think that the corrosion current or the corrosion are contributed by rainfall. And after 10 days, after the corrosion products have been gradually forming, we see a sharp increase of the importance of corrosion of the humidity and a concurrent simultaneous decrease of the importance of the rainfall. And these two are becoming somewhat similar during the next 15-20 days of corrosion tests. And recognizing the importance of corrosion product formation on the output current, we introduced a new term in a model called electrical quantity, which is the summation integration of the instantaneous current over time. And it's representing it's reflecting the amount of corrosion product that are formed during the 1 minute. And the variation of the importance of corrosion product, we can see it's really following the same trend with the variation of humidity, which verifies our series. And these are showing the comparisons of the models that include just rainfall, humidity, and temperature, and the model with inputs that incorporates the electrical quantity or the rust formation as the forest parameters. We can definitely see that, again, compared to neural network and support vector regression, random forest models are better in terms of the accuracy. And also, the model that consider rust formation shows significantly improved the prediction accuracy. And next, we treated the model in this way. We developed a random forest adaptive iterative model to predict the dynamic process of atmospheric corrosion. So for this model, we split the data set in two parts. The first part contains 25 days of data for training, and the second part is 5 days for testing. And the 5 days of modeling, the first minute, the inputs are the instantaneous rainfall, instantaneous temperature and humidity, and also the electrical quantity, which is the corrosion product that are formed during the last 25 days. The output of the current this model was the predicted corrosion current. And after we get the predicted corrosion current, we multiply the current with 1 minute and convert it into the corrosion product that are formed during this 1 minute and add it back to the corrosion data, add it back here, and use this new term as the new input for the modeling together with the instantaneous rainfall, temperature, humidity at the second minute, and to predict the corrosion rate for the second minute. And we do this iteratively, cycle by cycle, which reflects the dynamic variation of the atmospheric corrosion process. And we can see that after the model corrected with the rust formation, the accuracy was substantially improved. And also this model gives us some idea that once we have collected enough corrosion data, and the model really depends just on the environmental factors, and all the currents are predicted, and which is quite meaningful for the corrosion monitoring, because that way we can just use cheap and simple humidity sensor, temperature sensor, thermometers, and also the climatic data for instantaneous corrosion real-time corrosion prediction. And this is showing the data from a 1 year long corrosion monitoring test, and we process them using similar methods to get to quantitatively compare the corrosivity of the atmosphere in different parts of China. And in the last example of my talk, it was somewhat different from the previous three. The data are not generated by us mostly, but they are obtained from papers by crowdsourcing, and it's for the prediction of corrosion inhibitor performance based on a molecular graph model. And corrosion inhibitors are the way of dealing with are organic molecules, and basically there are infinite number of molecules that can be used as corrosion inhibitors. So it's really important to have an efficient screening method to identify for the corrosion inhibition efficiency of different molecules. But so far, the effectiveness of these type of screening models have been limited to a specific class or categories of inhibitors that have similar molecular structures, and does not have a good generalizing ability that can fit for molecules of different molecular weights or structures. And to solve these problems, we're establishing a 3-level molecular graph model that integrates atomic level feature, the chemical bond level feature, and molecular features for the prediction of organic molecule as corrosion inhibitors for carbon steel. In this case, it's a 1 molar hydrochloric acid solution. And the data are from 113 papers, and we have obtained 270 corrosion inhibitors. Once we have the original data, we convert them into a SMILES form, which is really a machine or a more computer readable way of representing molecular structures. And the graph on the right-hand side shows that the distributions of molecules of the 270 molecules in terms of their molecular weights and also their categories, which shows that our data sets are sufficiently diverse without obvious aggregation of the data, which is really important for construction of a predictive model that have a high generalization ability. And we compared the model that we developed with a support vector machine, a random forest, and also the models that are based on just the molecular feature, just the atom feature and the molecular feature. And we can see that the three-layer model shows the highest accuracy among the three. And by comparing these two, we can definitely see that the inhibition efficiency of a molecule is not just related to the bond, to the atoms, but it also is related to certain molecular features of the molecule. And this is for the testing, we use different data sets. For training data sets are for publication from, I think it's from 2010 to 2021. But for testing, we use recently published torsion inhibitor data from within this year, and also some of the molecules are obtained from laboratory tests conducted in my own laboratories. And we can see that the model exhibits a good generalizing ability and make reliable prediction for molecular categories that even outside the training domain. And it fits, and these each point represents one type of torsion inhibitors, and there are having different molecular weights. So which shows the model, this model have different have the ability that can it's a universal model for molecules that have different weights and structures. In summary, following the works that I introduced above, we are in the process of creating a 5th generation of torsion database, which is really a MD-friendly and ready big data platform that integrates data evaluation, data fusion, correlation, data-driven multi-skill calculation predictions as well, and for different type of materials. And these are some of the modules that we have developed so far to predict the atmospheric corrosion of different types of materials in China, and also to sharing and analysis of the online monitoring data. And such type of platform has been used already for different industry sectors like the energy transmission, railway, museums, underground pipeline networks, and offshore platforms. And finally, I would end my talk with a summary like this. We believe that data-driven approaches are quite important and helpful, especially for corrosion researchers and engineers, because we can deeply understand the mechanism. We can help us to more deeply understand the mechanisms of complex environmental factors affecting material degradation and performance. It can substantially shorten the evaluation period for material service performance, and it can help us achieve a more rapid prediction of material service life, and also it can support the optimization of design and rapid application of better, newer, more advanced, longer life materials. And these are my colleagues from the materials department, and also my colleagues from the computer science department. And thank you. And I want to do a quick advertisement of the center that I'm in. So the Beijing Advanced Innovation Center for Materials Genome Engineering is the data science is only one track, but we're also dedicated to recruit people that are working on computation and high throughput experimental techniques, and the degradation and also database development and data technologies. And thank you again for the invitation. And it's thank you.
Thank you very much, Professor Dawei Zhang. I think I'd like to ask everyone to join me for a big round of applause for Professor Zhang's presentation. Thank you so much. So I think we have a few minutes for some questions and answer session here at the end of his talk, where we've seen such a tremendous effort in gathering the big data on corrosion, and how Professor Zhang and his co-workers in China has used the tools together to predict the composition structure for the corrosion environment. So if Professor Zhang can answer some questions, and here now, anyone has got some question for him, please just raise your hands or turn on your microphone to speak. Thank you. Any question from the participants?
I have a question. Hi, Professor Dawei. Good to see you. It's a very impressive talk and very inspiring for the work, advancement of the work in this field, because it's also related to what we are doing right now in terms of corrosion monitoring of the atmospheric corrosion. I have a few questions. When you talk about the electrical quantity, is it the same as the cumulative charge?
Yes, correct. I think it's exactly the same.
Okay. And another question is the corrosion map of carbon steel in China is very interesting. Can you show your slide on page 25 again?
Okay. This one?
Yes, this one. There is a high corrosion rate in the area even further from the seashore. What are the main factors that causing those kind of high corrosion rate?
Yeah, I think actually this is a Sichuan area. The geography is really a basin of China. It's a low altitude surrounded by a lot of mountainous areas, and it's actually one of the hottest areas in China. And it also has a lot of rainfall and high water condensation. Even though it does not have a lot of, and make it even worse, it does not have a lot of sunshine. So which keeps the moisture and keeps the water condensation that can lasting for a very long time, and that's the reason why this part is really highly corrosive.
I see. Very interesting. Thank you.
Thank you, Anita.
Okay, have you got any questions from other participants? Please just turn on your microphone and speak now. I think we have maybe 2-3 minutes more for some questions here. Yes, Dr. Teck Liang, please go on. Go ahead.
Hi, thank you, Prof. Zhang, for a very interesting talk. Yeah, are you able to share with us if there's any also, if you have worked with, let's say, collaborators with computational data, is there some demonstration that shows that computational data, let's say when it is used together with your experimental data, can also help to develop better machine learning models for corrosion predictions?
Yeah, I think, Dr. Tan, I think, thank you for the question. I think it's a really important initiative that you just mentioned. Actually, so far, we don't have such kind of a personnel or capability of or experience with linking the computational data with corrosion modeling, at least not within my lab, because the data that we have collected historically are all based on the long-term exposure test, coupon test, or the monitoring test. And the lab develops from really a testing lab or experimental lab towards data sharing, and then towards data mining and data application. So it's transiting from a physical lab into a digital lab. And the origin of this lab existed way before the Materials Genome Initiative. But we have just hired a couple of guys that are that have extra expertise, backgrounds with materials composition, and we're planning to develop like really automatic workflow that can link machine learning, and also that can use machine learning to link computational methods from DFT, MD into experimental corrosion data for a more holistic model, holistic prediction.
Okay, thank you. I have a second question. So based on your machine learning, so I believe you use different kinds of features, including maybe composition, maybe environmental features. So which are the important features that you found that really is very correlated to the corrosion data?
If I think for different corrosion processes, the answer is quite different. But for most of the atmospheric corrosion tests, the important data are rainfall for the very corrosion initiation. It kind of like starts the corrosion, and then the humidity temperature kicks in, and also wind plays quite a good role. And if it's a coastal area, the chloride deposition, the salts that are blowing from the sea to the seashore and to the inland area, this is also quite important. And also, if we were thinking about corrosion in a real outdoor environment, and even in altitudes and the geography, and for example, if it's surrounded by mountains and that kind of thing, also are quite important for corrosion. But if it's for among the compositions, chromium, I think manganese, nickel, definitely I think iron will be the top few elements that are important. But this is the complexity of corrosion machine learning model is really that it depends on the interaction between the environment and the materials, and over time it creates a surface layer that's kind of a ceramic that combines where the composition effects and the environmental effects are meeting each other together.
Okay, thank you.
Okay, thank you, everyone. I think I would like to end our first half of the session there. Thank you, Professor Sang. And now we have a break until 3 o'clock, and where we will start the next talk by Dr. Nongnut Adrit. Yes, we'll see you there in about 7 minutes. Thank you.
Thank you.